One of my go-to podcasts these days is the excellent Let's Learn Everything. They really do cover almost everything, from serious science topics like super heavy elements to silly miscellaneous topic like the art on postage stamps. But I'm especially fond of whenever they do a math topic, like their recent episode that included a section on unsolved math problems. Now, this episode had a huge range of things in it, mostly focusing on serious problems like Fermat's last theorem and other unsolved problems. But they had this one throwaway line about Pythagorean triples that sent me down a rabbit hole and is the basis for this entire video. Let's watch what they say.
So 3 to the power of 2 plus 4 to the power of 2 equals 5 to the power of 2. 9 plus 16 equals 25.
That makes sense.
Makes sense. All whole numbers. This is actually a Pythagorean triple. So, in a right-handed triangle, the square of the hypotenuse, the side of the triangle,
a²+b² equals c².
opposite the right angle is equal to the sum of the squares of the two sides. a² plus b² equals c², as you say, Tom. This is Pythagoras' theorem, right? And in fact, there are an infinite number of positive integer solutions for this equation. A, B, and C can be an infinite number of positive integers.
Whoa.
Okay, this has been well known since like Babylonian times.
Right, and we both knew that, right, Ellen? Since Babylonian times, I knew that.
That's right, Tom. Not only does a² plus b² equals c² have infinitely many integer solutions, which is maybe surprising enough, but they can also be arranged in this beautiful grid where the 3, 4, 5 triangle we saw is the very tippy of the grid, and it goes on forever in an infinite number of rows and columns from there. Now, in every single row and column here, you'll find some cool patterns. So for example, if you look at this first row, the bottoms go 3, 8, 15, 24, 35, 48, and so on. Maybe you can see the pattern. But actually, there's one pattern that just generates the entire grid. And up to multiplication by some constant, like doubling the size of the triangle, this is actually every single possible Pythagorean triple. This is some very, very beautiful mathematics, if you ask me, and it is a shame that it's not taught in every single grade school in the world, but here I am to teach you about it today, and I'm going to show you the math behind this grid and where all these things come from. Now, as mentioned in the podcast, this is not new mathematics. This has actually been known since the Babylonian times. And in fact, there's this infamous tablet called the Plimpton 322 clay tablet, discovered by this guy, Edgar J. Banks, who a lot of people think is the inspiration for Indiana Jones, that has a bunch of these Pythagorean triples listed on them. This tablet is basically a spreadsheet, and it has 15 of these triangles written on them. On row 4, they have this sucker, 12,709 squared plus 13,500 squared equals 18,541 squared. And a lot of people think basically because this tablet has such large Pythagorean triples on there, the ancient Babylonians must have known this pattern for all the Pythagorean triples. Now, actually, this tablet really sent me down a rabbit hole. I spent a lot of time researching it, and I've added a little bit of extra details about this tablet at the end of the video. So if you're into archaeology, stick around for that. But for now, let me show you the pattern in the mathematics. And the starting point for all of this is the humble binomial, x plus y, everything squared. Depending on where you went to school, you might have learned different ways to expand this out. Where I went to school, we learned square the first term, then square the last, and then double the product, math's a blast. That was a little rhyme we learned. Some people learn it as FOIL, first, outside, inside, last. However you want to do it, you should get this nice formula, x squared plus 2xy plus y squared. And it's not just algebra, there's actually a really nice picture proof of this. You can draw a square with side lengths x plus y by x plus y and break it up into an x and a y, and you'll see that we've divided it into 4 pieces. That top square in the corner has area x times x, which is x squared. In the bottom corner, we have y times y, which is y squared. And then these 2 rectangles, each of them is an x and a y. It's got an x times a y and a y times an x. So if you add it all together, well, you got x squared plus xy twice. That's the algebraic formula. Now you can see how to do it with geometry. So even if you don't have algebra available to you, you might understand this formula just through this geometric picture. That might be how the Babylonians did it. Now, if you have x plus y squared, you might also have a formula for x minus y squared. It's going to be the exact same thing. And algebraically, it's very simple. You just end up with a minus 2xy instead of a plus 2xy because you have flipped the sign on the y. Now, if you stare carefully at these 2 formulas, you might notice they're actually extremely similar. The only difference between x plus y squared and x minus y squared is this plus to minus 2xy. And that means if you subtract them, you do x plus y squared minus x minus y squared, you get a very simple formula, which is just 4xy. If you rearrange this formula and put the x minus y squared on the left-hand side, now it says x minus y squared plus 4xy equals x plus y squared. And this one also has a really nice picture proof. You can think of it with the same square we had before, but now make 4 copies of that xy rectangle, and you'll see that the big square of side length x plus y squared, has now been subdivided into 5 parts. There's 4 xy rectangles floating around, and then there's that little tiny square in the middle that is x minus y squared. if you add x minus y squared to 4 copies of xy, you get x plus y squared. So even if you don't know algebra, maybe you have discovered this formula through this beautiful picture proof over here. Now, however you want to do it, once you get this formula and you stare at it, you should figure out this is extremely close to a Pythagorean triple. X minus y squared, well, that's something squared. X plus y squared on the other side of the equation, that's something squared. The only thing that is stopping us is that stupid little 4xy in the middle. If only 4xy was something squared. If 4xy was something squared, then we would be happy. We'd have x minus y squared plus the something squared equals x plus y squared. And you can do this by a little trick called plug in the thing that you want. If we want 4xy to be a square, just plug in x is a square number and y is a square number. If x is some square number, r squared, and y is some square number, s squared, and you plug those into our equation, what do you get? You get exactly what we wanted. The middle term becomes a square. It's 4r squared s squared, which is exactly the same as 2 times r times s, everything squared. So you have this nice equation, r squared minus s squared all squared, plus 2rs all squared equals r squared plus s squared, everything squared. So this gives you a Pythagorean triple. And what we've said here is that if we call this thing A in the beginning, call the middle thing B, and we call the big number C, then we have found a solution to a² plus b² equals c². It's solved by plugging in these particular values of r and s in this particular way, and it kind of goes with this little picture. Now, if you write down all the possible values for r and s, and you put them in a big grid, I made r the value in the columns, and I made s the value in the rows. I started over here at r equals 2 and s equals 1. That's the classic 3, 4, 5 triangle. But if you leave s equals 1, you get that first row that I was talking about. And you'll notice at the bottom of every triangle is just 1 less than a square number. So 8 is 9 minus 1, 15 is 16 minus 1, and so on. It's all coming from r squared minus s squared when s equals 1. And by doing this, you can get this entire triangle of all Pythagorean triples. You can prove that this is all of them. There's not some huge amount missing, except for the fact that you sometimes need to multiply these triangles by 2 or by half. You need to scale them up or down. So this is all the possible triangles up to scaling. There's a really nice 3 blue 1 brown video that has this result. I'll link it in the description. But going back to the Babylonians, the example I showed you before from the Babylonian tablet, they were plugging in r equals 125 and s equals 54. Now, these are not purely random numbers. These have some significance for the Babylonians. In particular, 125, you might notice, is a power of 5. That's going to come up. But if you plug that in into the formula that I just found, you get exactly what is on row 4 of this tablet. And all the other rows also have a different Pythagorean triple on them. And that's why we think the Babylonians must have known this formula and that they were sort of generating a bunch of these things and writing them down in this particular order for some reason. But what exactly is written on this tablet? Well, I'm not an expert in archaeology or anything like that, but I've been researching this for a little bit and I got really excited by this. In particular, there are a couple mistakes. So this is like looking at a student's homework and you find some mistakes here and there, but the mistakes kind of reveal what the student was thinking. And so by looking at the mistakes on this tablet, we can kind of get into the minds of the Babylonians who wrote this 4,000 years ago and figure out maybe what they were thinking. And that's what I want to show you now, what actually is on this tablet. So let me tell you what I've learned about this little Babylonian tablet. And again, I'm not an expert on these things, but I'm just excited to share with you what I've read about in a few different papers. All my resources are listed in the description below. So first of all, I always thought of this as some giant tablet that you would carry around and that someone had to hammer out with a chisel, but it's actually a very small sort of index-sized tablet, about 13 centimeters by 9 centimeters, and it was probably written by one person who was holding it in one hand and using a stick to make all these little markings into wet clay that then dried and became the tablet we have here. We know it's about 3,800 years old, so about 2000 BC when this was made, and there are other tablets that are very similar to this from this guy's Plimpton's collection. So Plimpton had a collection of thousands of these artifacts, and when he died, he left his collection to Columbia University, and this was number 322 in the collection, and it has since become a really famous artifact that a lot of people have studied and have been trying to decipher what these mathematical things could be and what were they used for by the Babylonians. If you look at it carefully, you'll notice it's divided into columns. In fact, it looks a lot like a modern-day spreadsheet. You might also notice in that far right column, there's a big chunk missing. What was missing there, and what did it say? Well, fortunately, that rightmost column is a very sort of boring column. It just says, this is row number 1, this is row number 2, this is row number 3, and so on. I've labeled row number 4, which is the row that I'm going to talk about mostly. And the good thing about this row, first of all, it's good that it was there because when it broke off, we didn't lose any actual information. But second of all, there are many other tablets that have the same exact numbering. So they're always numbered number 1, number 2, number 3. And therefore, we can sort of relate this tablet to other tablets of that time period and kind of combine them to learn more about what these guys were working on. The next two columns are the ones we're most interested in as mathematicians. They are the numbers that are part of a Pythagorean triple. So there's what I called A and C in the rest of the video. And in the marking at the very top, there's some words that are not fully translated and people are not 100% confident what they are, but there is the word width in the second column and the word diagonal in the third column. And that is where these big numbers, 12,709 and 18,541 that I mentioned in the video, that's where they appear. Now you might say, okay, well, those are the two columns. They got A and C, they're missing B. So surely that first column over here has B in it, the third number you need in the Pythagorean triple. Well, unfortunately, no. So the things that are missing from this spreadsheet that, if it was a modern day thing, we would definitely put there are the number B, so 13,500, and also these numbers R and S that I mentioned, 125 and 54, that kind of generate the A, B, and the C. They did not write these down. So actually, there's some speculation, what actual algorithm did they use to calculate these numbers? We know they must have had some kind of systematic way to do it to get these 15 to work, but what exactly did they do? Some of the details are missing. And actually, on the left-hand side of the column, there is a break. So there is a broken bit. And so it could be that there was another column. People don't think it was wide enough to contain all of this information, but it is interesting to think, oh, maybe there is something else there, and maybe one day we'll find another one of these tablets that has more information on it. Okay, but if the number B is not itself on the tablet, how do we know they actually had the Pythagorean triple? Maybe they only had 2 out of 3 numbers. Well, actually, this first column contains a ratio involving B. What it contains is the ratio C over B squared. And because it's a Pythagorean triple, that's also the same as A over B squared plus 1. And so in the fourth row with the numbers we've been working out, if you take 18,541 and you divide it by 13,500 and you square it, you get this number, 1.886, and so on. And in the heading for this column, there is something like the square of the diagonal. And once again, the translation isn't perfect. We're not 100% confident with what exactly they meant by this, but it is something along those lines. And so what we think is that because of this column, that they were actually thinking of these things as being related to triangles that have been normalized to have a base of 1. So by dividing everything through by that B value, they have made it so that the base is 1. The thing they care about, the C over B, that is the length of the diagonal in this normalized triangle, and the width, the A, that tells you how tall the triangle is. So some of the triangles were taller and some were shorter. And in fact, we know this must have been important to whoever made the tablet because the tablet is in the order of these diagonals. So it starts out with the tallest triangle and it kind of works its way down. So it's got 15 of these triangles really. And you can think of, these were the 15 triangles that I've drawn up here. Those are the 15 triangles that are listed on this tablet. Some are very tall and some are very short. So that seems to be the thing they cared about in column 1. Now you might say, hey, this is horrendous. Why would you ever divide? You have this Pythagorean triple and then you turn it into this really nasty ratio, 1.886247 ... and so on. That seems totally crazy. But this is where the details come in, and this is where I was really excited to read about this stuff, is because the Babylonians were working in base 60, they did a very nice trick, is they made sure that the values R and S that they used only ever had factors of 2, 3, and 5, and that means it would always be some divisor of 60. And by doing that, that means when they do the ratio over here, when they did C over B, it was always a sort of a nice decimal fraction that would end at some point. Now, we're not used to this because in our decimal system, there's only 2 numbers that you can make that are like this. There's 0.5 and 0.2. Those are the only 2 numbers that sort of have terminating decimals that are sort of a nice way you can take a fraction and turn it into decimals nicely. But because the Babylonians were working in base 60, they have these extra factors of 3 they could use, and they could do all sorts of things. And so every single number here, it is a decimal, but it's a decimal that ends, just like 0.5 and 0.2. So that is what we think they were doing. They were calculating the value of these triangles for the triangles where the decimal terminates, where C over B is a terminating decimal, and when you calculate its square, you get some nice number that maybe they were using for something. So some people have speculated that this is a kind of trigonometric table based on this C over B thing. Not everybody agrees with that. People think it had different purposes. Some people think it was maybe just an exercise, like somebody gave it to a student to work on and things like that. So there's not 100% consensus on what it was used for, but maybe it was something like that. And the thing that really sucked me in was the mistakes on this tablet. There are some errors, and the errors let us see into the mind of the person who made it from 4,000 years ago and let us think about what they were doing. My first favorite error here is on row 13. So in row 13, they wrote 289 as the diagonal. This corresponds to the Pythagorean triple where B equals 240. And what they wrote in the column for the width, they didn't write some number in the 300s, where 240 squared and 289 squared should be something in the 200s squared. They wrote 25,921. Why would they write such a thing? Well, it turns out that is the right answer squared. So they, instead of writing down 161 like they were supposed to, they wrote down 161 squared. They were off by a whole square. Now, if they were just writing these numbers down and they were calculating, you would never make this mistake. The only way that this mistake makes sense to me is if they had a second tablet or something and they were copying the answers down and that tablet contained more information. So in addition to having A and B and C, maybe it also wrote down a squared as a sort of intermediate calculation. And indeed, if they calculated the diagonal by doing a squared over b squared plus 1, this would make perfect sense. So if the method they were using to calculate that first column was take a squared, then divide that by b squared, and then add 1, then maybe they have a squared written down as a sort of halfway computation, and then this mistake makes perfect sense. I think that is a very plausible reason this mistake could have been made. Again, there's other possible explanations, and there's lots of errors on this thing. I think there's like 6 errors. So you kind of want a theory that explains all of them. I'm just going to go through a few of them here. Another error on this tablet that has been widely debated is in row 8. And in row 8, they got the numbers exactly right. So it's 799 and 1,249. Those are parts of a Pythagorean triple with 960. Those parts are perfectly correct. But what they wrote in the first column is the decimal numbers 1.69277 and so on. Again, this is a perfect rational fraction in Babylonian base 60 mathematics, and that is not quite right. The real answer is 1.69270. So they sort of made a mistake in like for us, the 5th decimal place. In the Babylonian system, it's like in the 3rd decimal place. They got the first 2 right, but then they made a mistake later on. And you might say, okay, who cares? I don't know, some guy just made a mistake. But once again, you can try to reverse engineer what the scribe was doing and figure out how he was calculating these numbers, right? And in particular, I think there's a very plausible way that the mistake could have been made, a very common mistake that was made with numbers in this time period, and it's related to this a squared. So if they were using this a squared calculation that I told you before to calculate the first column, then it all makes sense. Let me show you what that is now. And to understand the details, you have to understand how the Babylonians were writing in clay and what were the number system they were using, because that is going to explain where this mistake came from. So let me do a little detour now and tell you how did the Babylonians write numbers in clay. There's also a really excellent Numberphile video where they really have a piece of clay and they're doing it. I'll link that in the description as well. But essentially, the numbers 1 to 9 were very simple. Numbers 1 to 9 were a number of vertical dots. So they had their little reed or their little stick, and they were poking in a vertical line for the numbers 1 to 9. This is how they would arrange them. So by the time they got to 8 and 9, there would be some sort of like grid, so you could sort of easily count them quickly. But the numbers 1 to 9, there's no special symbols. It's just a stick, and the number of times you draw the stick is the number we're representing. The things get interesting for the tens. So the numbers that are multiples of 10, they would take their stick and turn it sideways and put a corner of it into the clay, and that would leave a sort of little corner shape. So for 10, 20, or 30, you would do 1 or 2 or 3 of these corners. Once you know how to draw the numbers 1 to 9, and you know how to draw multiples of 10, you can draw any number between 1 and 59 by smashing together the 10s and the 1s, just like we do in modern day times. So for example, here is the number 11. 11 is 1 10, you draw with the corner of your stick, and 1 1 you draw as a vertical line, and you put them next to each other with the 10s just a little bit to the left of the 1s. So there is 11. Here's another one. This is 21. So it's 2 copies of 10 and 1 copy of 1. And now I said this is only for the numbers 1 to 59. Of course, you could, in principle, keep going after this. You could say, I'm going to draw the number 100 by drawing 10 individual corners, but that is not what the Babylonians did. So they had a base 60 number system, and so beyond 60, they would start again and draw everything with place values. So they would draw the number of 60s and the number of leftovers as 2 separate things written left to right, just like our modern number system works in base 10. So to give you an example of this, what they would do is they would write a number like a times 60 plus b as a and b next to each other, where a and b are numbers from 1 to 59. I think the best way to understand this is an example. So for example, the number 70 is 1 group of 60 and 1 group of 10. So you would write that like this. You would draw a 1 on the left that would represent a group of 60, and then you would draw a 10 to the right of that would represent a group of 10. So that is 60 plus 10 because they are drawn in the opposite order as the 11. So the order matters, and it's a true place value system, with the place value being 60 once you get beyond here. So another way you can totally think of this is there's a symbol for the numbers 1 to 59 that is drawn in the way I described up here. And then once you have the symbols for 1 to 59, you drew an actual base 60 number system with those symbols below. Very simple, very nice. Let me give you another example. Let's take the number 1,201. Well, 1,201 is 20 bundles of 60 and 1 left over. So you would draw it as 20 times 60 plus 1. You would draw 20 to represent the first digit, and then you draw 1. So it would look like this. There's a 20 and there's a 1. And now, if you're looking carefully, you see where the problem is. 21 is 2 10s and a 1, and 1,201 is 2 10s in a place value and then a 1, and those look extremely similar. The only difference between 21 and 1,201 is how close you draw these digits together. So because they were using this combination of digits of 10s and 1s to make their individual digits, and their individual digits don't look different than each other, you could have these mix-ups where, because the place value is not quite right, you can get mixed up on what's going on here. In modern times, we have solved this with the notation for the number 0. So if they had drawn 20 as 2 10s and 0 1s, then it'd be less likely to make this kind of mix-up. You know, if they have like a dot, which I think they invented some thousands of years later, then they wouldn't mix these two things up. But it's exactly this mix-up between a 21 and a 1,201 that is an error in row 8, or at least one possible way you could get the error. So here it is. Here's a possible explanation for the error in row 8 of the Plimpton 322 tablet. So first of all, in what is written in row 8, well, there's this number A, which is 20 60s and 49 left over, what we would call 799 in our modern decimal notation. And if you square the number 799, you get this number 638,401, which is written in their notation. It ends with a 20, 1. So it's 2, 57, 21. So you'd write the number 2, then 57, then 20, then 1, all next to each other. And that's the last two, the 20 and the 1. If you make a mistake and you accidentally interpret the 20, 1 at the end as a 21, then you don't get 638,401. You get 638,460. You're off by 59 because you've moved a 1 from the 1s column into the 60 column. That's an error of 59 that you've made. So very, very tiny error, replacing a number in the hundreds of thousands by being off by 59. But if you then use that to calculate the ratios that are in column 1, you do a² divided by b². Then instead of getting the correct answer, which you should have gotten, you will get the thing that is written on the tablet. So it's possible that if they were calculating this way, if the person who was calculating all these things did this calculation just like this, that they would have gotten the answer written on the tablet, and that would explain where the error comes from. The thing is, this kind of error is very common, and there's other, plausible explanations that lead to this kind of error. So this kind of moosh of a 45, 14 becoming a 59 is kind of crunching together two number places. There's other ways this could have happened. And there's an alternative proposal where they say that the thing that was used to calculate the tablet was fractions. And so if you do it with fractions, you do r over s squared plus s over r squared. This is another algebraically equivalent way to get the numbers on the tablet. And there is a way you can make the errors in that situation too to get the same kind of thing. So people are not 100% convinced on which way it is. Some people think it's one way. Some people think it's the other way. And I think it's a really exciting kind of area of research. Like I think you could do like your whole PhD on this one tablet and trying to figure out what they were doing there. I think it's so exciting that 4,000 years later, we can still like dissect your little mistakes. You're off by 1 part in 100,000, and where you're like, people 4,000 years later are pointing out and going, oh, maybe this is how they did it. I think it's so cool. Okay, I think that's all I have to say about the tablet and Pythagorean triples for now. If you like the video, you can subscribe for more random math stuff as they come out sporadically.